just means min or max. So if the question asks you to find any local extrema, that means find any local minimum or maximum. Does that answer that question?
Yeah, I just thought it was like something extra that I needed to do, not just the min and max.
Nope.
Okay.
Yeah, extrema are just min and max. The next question, which I'll start with the first question in the chat, is the extrema found in the second derivative? So finding min and max or extrema. Those come from the first derivative.
Okay.
We haven't done any that don't have a derivative of 0, but those come from the first derivative. So in the process of analyzing the graph, those 4 steps that we went through, the minimum and maximum do come from analyzing the first derivative.
Okay.
You can use the second derivative test to decide whether we're seeing a minimum or a maximum. But if we know like a sign chart of a first derivative and we have some x value where the first derivative is 0, and we know it's positive on this side and negative on this side, that automatically tells us that we have a maximum here. So we don't need the second derivative to find any extrema.
Okay.
First derivative and second derivative intervals. How do you know what the second derivative is?
So I remember there was where you could move, well, I was watching a video, and it was where you could move it was a line, a vertical line, and it would show, but I don't know exactly how to tell the difference between the first derivative and the second derivative with it just saying it's less than or greater than, and the numbers that it's spitting out. I kind of get it, but not really.
I am not. Okay, let me try to answer your question and we'll see if I am actually answering it.
I don't remember us going over it in class, I guess is what I'm trying to say.
Okay, then I might not know exactly what you're referring to then.
Okay.
So the first and second derivatives will always come from the function that we are starting with. So you'll be given some f, and we can find the first derivative by just taking the derivative, and then the second derivative by doing the derivative again. There's no context in which we've had to like differentiate between first and second derivatives.
So when you're looking at a graph that has like a line, you know, that comes from negative and goes up and then down and then goes back up, and it's saying you're less than or greater than 0 at such and such point. Is this the one where it stops at the points if it only has a dot at the top and a dot at the bottom? And then if it has arrows, then you know that it's going infinity. Is that the lesson where we had talked about that?
If we were looking at something like that versus something like this, you mean?
Yeah, is that what that is pertaining to?
The first and second derivative?
Yeah,
Mm.
well, okay, so it is on, hold on, let me. Like on problem 2, where it says the intervals on which f prime of x is greater than 0. So how are you deciding whether it's a prime, a first prime or a second prime is kind of where I'm going.
So on something like number 2, and I'm just gonna draw a different kind of graph. We'll just say this is our graph for now. So this is the function. This graph is only showing us the original f of x.
Okay.
What do we know is happening on the graph if f prime is greater than 0? What is the graph?
Increasing.
It's increasing, exactly. So this one would be increasing from here up to here. So whatever that interval is, I'm just going to say this is a to b, would be the interval on which the first derivative is greater than 0. Whereas the second derivative being greater than 0. So the first derivative is talking about whether something is increasing or decreasing. So this means increasing. First derivative tells us if the graph is increasing or decreasing.
And the second is the concave.
Right, exactly.
Ah, okay. I gotcha. All right. I didn't understand putting it from one to the other. And I know we did it in the homework, but I wasn't understanding like why. So that explains why. Okay.
Yeah, so those, you're just going by the shape of the graph, really, what you're seeing is happening on the graph.
Okay.
Okay, so the other question that is in the chat is, do you find the local min and max through the critical numbers or partition numbers? So that's a good question. The short answer is critical numbers. But critical numbers are also partition numbers, but local min and max are always at critical numbers. And critical numbers are also partition numbers, but partition numbers can include things that are not in the domain. And so a local min and max has to be a part of the graph, which means its x values have to be in the domain. So they will always be critical numbers. And tell if there's a question or if that was an accident, unmute. Yeah, okay.
Sheree, I don't think your mic's working for some reason, hon.
Yeah, it just sounds like static. just sort of a random example. I'm just sort of choosing random. Oh, yes, it does. We need to use them in order to make the sign chart. So they can still divide like an increasing and decreasing sections. So once we find the partition numbers are what we would use to make up a sign chart. So maybe like these are both partition numbers. But maybe like one of them is not defined on the function, but the other one has a f prime of 0. So both of these are partition numbers because they're dividing up our f prime, and we can just assume we found these by setting the derivative to 0 and finding where it's undefined. So if, for example, this middle section was all positive and this end section was all negative, then this one is a max. It is in the domain because it has a value there. I'm just saying that for the sake of example. So this is a critical number. And since it's going up and then going down, that would be a maximum. This other one, it's still a partition number, even if it's not, if the function isn't defined there. So if, for example, we had like minuses over here, that's still changing, like our function is still changing from decreasing to increasing across that partition number. So it's still important, even though it's not actually a part of the graph of the function. It's like a little jump, but it's still important to use to make our sign chart. This one would look like an asymptote. Trying to think if it's possible that that would be a blip. You're not going to see any holes on this. Wait, let me look before I say that too confidently. Yeah, there are no holes on this test. But this would be an asymptote because this graph would be like decreasing on one side of this and then increasing on the other side. So it probably looks something like that. It's just a random example. These are good questions. Any other questions? We have 5 more minutes.
Madeline, do you mind just doing step 1 on the graphing? When you take all the permanent information and throw it into a graph, do you mind just doing step 1 on a non fraction? It could just even be a simple one.
A non-fraction, so something like a polynomial?
Yeah, a polynomial would be fine. If we could do one that's multiplying each other, so I'm still just kind of rocky on it.
Yes. So like 49 on the homework, that kind of one. So step one of the graphing process is analyzing all of the analyzing f of x, the original function. I think analyze is supposed to have a z, but so we have multiple steps to this. So on this one, we don't have a denominator, which means there's definitely no asymptotes. Asymptotes only come when we have a denominator that can equal 0. So no asymptotes. But we are going to have x and y intercepts. So first question is, what do we do to find a y-intercept?
Set it to 0. Or put 0 in for x.
Right, exactly. Put 0 in for x. So if we're doing a y-intercept, then x equals 0. Which in this case just ends up being 2 times -5. Gives us -10. Finding x-intercepts for this kind of thing. Oops, that's not what I meant to do. We have to remember algebra. So to find x-intercepts, we need to set the whole thing equal to 0. So finding an intercept always means plugging in 0 for the opposite variable. So now y is going to equal 0, which just means that whole thing will equal 0. So in this case, we would maybe want to factor as much as possible. We should factor as much as possible. The thing is, the x plus 2 is already factored, and the x squared plus 3x minus 5 doesn't factor anymore. There are no two numbers that multiply to 5 and add to 3. So that's okay though. We have this as factored as possible, so we can still break down these two factors into their own separate equations. And then we can just solve each of these however we can. This one is nice. Don't have to do much work for that. The other one, since that is not factorable, we have to think back to algebra and think of our options for solving something like this. Completing the square is one option that I am personally partial to. However, it's usually not that fun when we have an odd number in the middle. So the tried and true always works method is the quadratic formula. So we can solve this equation on the right with that quadratic formula. Plugging in A, B, and C. And then we would just have to simplify all of that. So inside that's going to be 9 plus 20. So we have 2 x-intercepts, or 3 x-intercepts, the -2 and the plus or minus from that quadratic formula. And that is all for step 1. We have the intercepts, asymptotes, oh, and the domain.
Would you be able to break that 29 into 25 plus 4?
No.
Correct. 29 is 25 plus 4, but that wouldn't help because it needs to be a multiple or a factor. So if it was 25 times 4, then that would be great. But 29 doesn't have any factors that are perfect squares.
So for this particular equation, or the x plus 2, would you just use the product rule to find the first derivative? Right.
Yes.
Okay.
So you can use the product rule, or the other option is to multiply it all out so it's just a polynomial.
Okay. Okay.
Either of those would work. So our time is up for our test questions today, but we will again on Tuesday have the first 20 minutes of class will be reserved for questions. Unless no one asks questions, and then we'll just continue. So the test is due on Tuesday at 11:59, so you shouldn't be coming to question time like with having not even looked at it. So definitely try to have most of it done by then, and then sort of last minute questions on that day. Okay.
Thank you.
Thank you, Madeline.
No problem. It was good questions. A lot of times when I do question sessions, no one asks anything. So it's nice to have questions. Okay, so we are continuing on in chapter 5 now. And so all of this, it was from Tuesday. So I'm just putting these back up so we can reference them as we are finishing up section 5.1 a little bit. So on Tuesday, we started antiderivatives and indefinite integrals, and we had these 3 basic rules. So we have the reverse of the power rule. So we're going backwards now, raising the exponent by 1 and dividing by the new exponent. We have our exponent rule, which is our E rule, which is just the same as the derivative. And then we have our natural log. So 1 over x has an antiderivative of natural log of absolute value of x. So we're going to start with just a couple examples using these, and then we're going to level up our integration skills in section 5.2. So picking up where we left off on Tuesday. So on Tuesday, we did some practice with integration where we saw that we need to get our integrand, which is what the inside of the integral is, get the integrand in a format so we can use those rules. So that basically means that we need to somehow simplify this inside stuff so that we have separate terms with x to some power, so we can use our reverse power rule.
X to the -2 to bring it up. Can you do that?
We can do that. And so it would be this. Which would be fine. but we still need to distribute that x. Actually, I don't know why I wrote that floating up there. Let me write this down here. So this is actually one way to do this. It's just not where my brain was going. But if we wanted to bring up that x to the -2, we can do that. And then we would have to distribute the x to the -2 into the parentheses. So if we distributed x to the -2 to x to the 4th, what would we get?
X squared.
X squared, yes. So we would add those exponents together. And then how about the second term?
8x.
8x, yes. So that is totally fine to do it that way. Bring up the x squared and then distribute. The other way would be to separate. So we have x to the 4th minus x, 8x cubed on top. And we could just separate each of those to be divided by x squared separately. In which case we would get the same thing.
I kind of like that one better.
And I messed up. Yeah, either way will work. So now our integral is x squared minus 8x dx.
So if the problem starts with the integral, does the answer start with the integral?
No, the answer should not have an integral in it anymore.
Oh, okay.
So in this case, these two
Oh, we're not
that
done.
are written, yeah, that first step was just simplifying the inside so that we can take the integral now. So nothing has actually changed here, it's just in a different format. And now we need to take the integral, which will be the rules that we were doing on Tuesday, which I'm just going to write the x to the n rule here. So just like derivatives, we can go piece by piece. So starting with this x squared, what is going to be the integral of just that x squared?
X cubed over 3.
Exactly, x cubed over 3. So we're raising that power by 1 and dividing by the new power. So then how about minus 8x?
For x squared.
Yes, and I'm just going to write it out in the steps just so we have them, but that is the correct simplified version. So we would raise the power by 1 and divide by that new power, but when we simplify it, that is going to be minus 4x squared. And you don't have to go through that 8/2 step. We can skip that step knowing that we're dividing by 2. But just so we have all the steps, I have it written. What is missing from these last 2 lines though?
The c, plus c.
Yes, exactly, plus c. So when we do an indefinite integral, so that's all of the integrals we know so far, we'll always have that plus c to take into account that if we went backwards and did the derivative, that c is going to go away no matter what it is. And that is our integral.
That first term is supposed to be x cubed.
Thank you. Okay, where did you go? There you are. Okay, so we did a little bit with radicals on Tuesday. So we have the same goal here to start off with, which is to rewrite this in a format that we can do our integration rules to. So we need each of these terms to be x to some power.
Eight x to the 1/3.
8x to the 1/3.
And 6 to x to the negative 1/2.
Right, exactly. So the square root is the 1/2, and then bringing it back up to be next to the 6 would make it the negative. So same kind of skills as we use for derivatives. We need it in this x to a power format. So here is where we need to be careful because now our n's are fractions. And so it's easy to just make little mistakes here. So we don't need to do scratch work over here, but I like to for class purposes to make sure we have everything right. So n equals 1/3 is the first term. So our exponent is 1/3, which means n plus 1 is 4/3. So I like to figure out what n plus 1 is going to be so that we can put it into our little rule. So the 8 in our first term is just still there. That's right. 8x to the 4/3. So we have n plus 1 as our new exponent, and that whole thing is being divided by 4/3, which is actually the same thing as multiplying by 3/4. So if I were doing this problem, I wouldn't go through that dividing by 4/3 step because we know if we're dividing by a fraction, we need to multiply by a reciprocal. So that's where we need to get to. And then the 4 and the 8 are going to cancel each other out. And we will end up with 6x to the 4/3 for that part. So then our other one, n is negative 1/2. So n plus 1 is a positive 1/2. So this second one, we have 6x is now being raised to the n plus 1, oops, which is 1/2. And it's being divided by 1/2. Dividing by 1/2 is the same thing as multiplying by 2. So in this one, we have minus 12 x to the 1/2. So as we get more used to integrals, for this kind of thing we saw up here, we probably don't have to do that much writing out to get to our integral, raising the power by 1 and dividing by the new power. But once we get fractions, it's easy to make little mistakes when we're not writing stuff out, which is why I encourage you to write out what is happening with that new fraction exponent and dividing by the fraction.
These problems are killing trees.
Yeah. It's true. Eventually, as a math student, I gave up on trying to save paper and just wrote to big because it makes a big difference.
It does.
Like
I'm
making
getting there.
mistakes. Yeah. Okay, so I am going to put up a link to just one more of this kind of integration practice problem with a fraction exponent. So go ahead and open that and try that one and put your answer in the box. If you have finished that one, I'm putting up one word problem that you can start looking at. But if you haven't finished this one or you haven't quite gotten it right, continue working on that internet problem. Okay. Let's- So going backwards, we'll come back to this word problem in a moment. Whoops, that's not what I wanted. Okay, so it looked like most people were like close, even if you didn't quite get it. There were some that were just missing plus C's, which is an important part of the answer. But so here, the n that we're starting with is that 5/6, which means n plus 1 is going to be 11/6. So when we put this together, we have x, which is being raised to the new power of 11/6, and then it's being divided by that new power of 11/6. But it's weird to leave it like this, so that denominator should flip and multiply. So we would end up with 6/11, x to the 11/6. And either that or 6x to the 11/6/11.
It accepted it the first way too.
Yeah, I think either of those is fine. Technically, this first way is also correct, but I don't like it that way. You should simplify fractions, which means flipping and multiplying. So either of these would be fine.
I don't know if I typed it wrong, but it said that I got it wrong. Oh, I did type it wrong. Okay.
Okay, yes, yeah, just barely.
I accidentally flipped the exponent as well.
Right. Yep. So we have our like 3 basic integration rules, which is this reverse power rule, our exponential rule, and our log rule. So we're going to do one application problem with this before we build on our integral skills. So I'll give you a minute to look this over first.
I guess 402.
402 for
B.
B. Okay. We will find out.
Well,
So we have this problem. The marginal cost of producing X units of a commodity is given by C prime equals that expression. So we have talked about marginal cost in the past. It's just the derivative of the cost, that's C prime. And the fixed cost is 2,000.
oh no.
So we have not talked about that yet, but we will get to it in a little bit. So we have two parts. Our first goal is to find the cost function C of X.
Are we finding the antiderivative on that one?
Yes, exactly. So if we integrate C prime of X, that will give us almost the cost function. So if we take the derivative of that, or excuse me, the integral, so if we integrate 0.3 x squared plus 2x dx. Just a little side note, I think the book usually puts parentheses around everything in the integral. I don't always do that just because the integral sign and the dx sandwich everything that's in the integral. So parentheses I feel are not always necessary, but they can help sometimes, I think, to show all of that stuff is inside that integral. So when we do that, we will use the rules we were just using. So if we raise this power by 1, I'll just write out the steps. Raise the power by 1 and divide by the new power. Same thing here. I'm not going to write C here because C is already representing cost, but we do still need that constant added. So I'm just going to use K instead of C. The letter we use to represent the constant is arbitrary. I just don't want to confuse it with the cost function. So when we reduce these fractions, we get 0.1 x cubed plus x squared plus some constant. So this gives us at least a starting point for our cost function C of X. The thing that we don't know, though, is that constant K. We need to find this. We don't have our full function until we know what that is.
It's not 2000.
It is, yes, it is 2000. So we do know what it is, we just didn't have it in the equation yet. So the fixed cost that we're told is the cost that does not depend on X. So those would be like, setup costs, rent, whatever, things that are fixed and do not depend on how much we are producing. So the fixed cost is going to be that K.
And then we just plug in 20.
Right, exactly.
So
So
add 2000 to my answer.
2000?
To my 400 and
Oh, I see. Okay. So yeah, so part B, we are looking for the cost of producing 20 units, which is something we've done before. So we're just taking that cost function we just found and plugging in the 20. should be did I do that right? Yeah. So I am getting 3,200.
I forgot my cube. Made a huge difference.
So last class, we talked about how an integral is going the other direction from a derivative. So in this case, in this kind of example, we have the derivative already. So the integral gives us the original function. The only thing that the integral can't do is give us exactly what that constant is. So if we need to know that C, we need a little bit more information. So that's why we're being told what the fixed cost is. Okay. So for derivatives, we had all sorts of rules. We had these first three rules that we learned, the power rule, exponential, and logarithms. Then we built a bunch of rules off of that, like the product rule and quotient rule and chain rule. I think that's all. We are not going to go as deep into integration as we did into derivatives, and that's because integrals integrals are way less straightforward with derivatives. Derivatives, we have like this finite set of rules, all of which we've learned, and those apply to everything pretty much. Integrals are not so straightforward. There are literally hundreds of rules for integrals that just most people don't need to know. But there is one kind of integration that is important, and it is it's the rule that's analogous to the chain rule for derivatives. So if we can use a chain rule to find a derivative, we can undo that with integration by substitution. So this is section 5.2. And we're going to talk about what this means in a little bit, but substitution is also known as U substitution, which I will probably say sometimes. And we'll find out why it's called that in a little bit. But so before we start in on U substitution, we're going to do just a little bit of chain rule review, brush off our derivative skills. So if we know g of x is 1/4 all of this, and we want to know g prime. So doing our exterior and interior functions for the chain rule. So e of I of x is that 1/4 I of x to the 4th. So our exterior is the stuff on the outside. And just I of x would be that interior part. So a chain rule, we're identifying the exterior and interior. E prime of I of X. So that 4 is going to come down and multiply with the 1/4, so those will just cancel and we'll be left with I of X to the third. And I prime of X is 6X. So it's probably been a few weeks maybe since you've thought about the chain rule. So we have our exterior and the derivative of the exterior and that derivative of the interior. So the chain rule tells us that we will have the derivative of the exterior, which is that interior part raised to the third power, times the derivative of the interior. And just for, because it looks nice, we can bring that 6X out in front. So this is just the chain rule of derivatives, nothing new here, just a little review. So when we use the chain rule to find a derivative, we have that main chunk from the exterior, the derivative of the exterior part, and then we also have that derivative of the interior part. So doing a chain rule will leave us with sort of these two parts. So part B.
Is that supposed to be to the third?
Yes, it is. Thank you.
Yeah.
This wouldn't work the way I planned if it was to the fourth. Okay. So now that typo is fixed. We're trying to integrate the thing that we just got as our answer in the first part. And so we don't actually have the technique to do this yet, but we can just do a little bit of thinking about what integration and derivatives do. This whole thing is G prime. So without even using those actual functions yet, what we're looking at is the integral of G prime in the previous example, we integrated C prime. We integrated the marginal cost. So when we take the integral of a derivative, that gives us the original function. Plus C, because it's not able to give us exactly what that original function is. So here, oh, sorry, go ahead.
So does it basically go back to that 1/4, 3x squared plus 5 to the fourth?
Yes. So this whole
What?
thing is going to go back to that original function.
And then plus C.
Plus C, yeah, that's the only difference. So we will actually have a real technique to do this without having to see the derivative first. But this is what is happening when we do an integral. It's just sort of going back and forth between the derivative and the original function. So taking an integral of a derivative gives us that original function plus c. So the thing to highlight here to see that will give us our substitution method is that we had this sort of complex function in our integrand. And there was also a piece on the outside that happened to be the derivative of something on the inside. So in order to use this substitution method, which we're going to get to, we have to sort of think backwards from the chain rule and know that the chain rule gives us those two parts, our derivative of our exterior and that little derivative of the interior. So that little extra derivative is sort of a key player in integrating things like this.
So if we are going backwards, I mean, I'm assuming that the c is plus c is there because we're supposed to be like losing information when we find the derivative of the original equation. And the c is there to represent the lost information, correct?
Yes, exactly.
So so if we look at the integral compared to the original function g of x, why all of a sudden do we get an extra constant?
Because so this g of x that we started with has the derivative g prime, which we found. But so do, like, if we had a plus 10 at the end of this is some other function, that also has the same derivative as that g prime. So the integral, if we're just starting with the integral of this inside, it is the integral of g prime, but it's also the integral of this h prime. It could be the integral of lots of other functions.
So could that c also be like a plus 0? Is that what you're saying? The constant would be there?
Yes. So in the case of this original g, there is a plus 0 there, which is not written, but that would be the c on that function.
Okay.
Yeah, that's a good question.
Is there a way to just know that all you need to do is add a plus c as opposed to going through the chain rule?
Well, we always need a plus c if we're doing an integral, no matter what. I'm not sure if I answered your question.
It just seems like you're starting with something, you're going through the whole thing, and then you're going back to what you started with. Is there a way to know that you don't have to do, that it's going to be this type of equation as opposed to having to go through the chain rule and do all those steps?
Yeah, so when we're actually doing the U substitution problem, we are not going to be starting with the chain rule. This was just an example to tie these two ideas together.
Gotcha. Okay.
But we won't be starting with a derivative, we'll be starting with just the integral part. But integrating in this method that we're going to do today is the analog to the chain rule. So it's undoing a chain rule that we did not do in the first place. So let's get into this method so we can actually see where we're going with this. Before we do that, we need to talk about one little thing called differentials. So before we say exactly what a differential is, slope, if we use just the standard Algebra 1 definition of a slope, it is the change in y over the change in x. Which a lot of times we express as delta y over delta x. So delta, which is this little triangle, just means a change. So that you'll see in science classes as well. The way we have been talking about slope in calculus terms, though, has been, dy dx. So when that change in y and change in x get infinitely small, we now have the concept of slope at a point with an infinitely small change in y over an infinitely small change in x. So dy is a tiny change in y, and dx is a tiny change in x. So it's like we're taking slope and making those changes infinitely small, which is what we saw when we first defined derivative. We saw that the derivative is the limit as the change in x goes to 0 and the change in y follows along with it. So differentials are these dy and dx values. Even though they're not really values because they're infinitely small, we can think of each of these as teeny tiny change in x and y. And their relationship comes from the fact that dy dx equals, let's say it's f prime, if y equals f of x. And so far in this class, we have always been using dy dx as one thing, which it is. Represents the rate of change. But it is also two separate things that we can separate using algebra. So if we multiply both sides by dx here, dy is equal to the derivative of the function, whatever that is, times dx. So even though both dy and dx are infinitely small values, they still have like a very specific relationship with each other, which is why they can give us the slope of the tangent at any point on a curve. And so these two little things are differentials. Finding differentials, we don't need any new tools. It's just a matter of finding the derivative. The only difference is that we are moving that dx to the other side. So instead of looking for dy dx equals the derivative, we're going to find dy, which equals the derivative times dx. So let's look at this first example. So we're going to find the following differentials. So we want to find dy for y equals x cubed.
So 3x squared dx.
Exactly, yes. So dy equals, so we just take the derivative of that function, x cubed, which is 3x squared. And the dx is over here now. So the derivative is actually the same. No new derivative rules at all. It's just that that dx has multiplied to both sides and moved over using regular algebra.
I'm sorry, Madeline. Oh, never mind. You're okay.
So now instead of y equals a function of x, we have u equals a function of x.
Well, this looks like a chain rule.
It is a chain rule.
Okay.
So what is the derivative of a natural log of something?
1x.
1 over whatever is in that natural log.
Oh, yeah.
So I'm sort of,
Fast forwarding.
yes. And then we have the derivative of the interior.
X.
2x, exactly. And dx at the end. So that was the derivative of the exterior, which is the natural log, times the derivative of the interior. And so we have our du. So derivative rules are exactly the same. It's just that little dx is on the other side.
What's the purpose for it? The differentials.
Yes, good
That's
question.
what we're getting to.
Yeah, I mean, there are a lot of purposes. So one, you might notice that this little dx that's on the end of all of these has been showing up in all of our integrals. Our integrals always have a little dx at the end. So next week, when we talk a little bit deeper about what another interpretation of integration, that little dx is going to be important. Yeah, and it's going to be important in this substitution method. But really what this statement is saying is that for this function, the change in u in this case depends on the amount that x changes, which is multiplied with this derivative part. So the change in the y depends on this little tiny change in x with the derivative on it. Okay, so let's use these little differentials. On page 335, there's another one. these three rules are exactly the same as the rules we had before. The only difference is that now instead of having an x as our variable, we have a u. So u can be a variable, or a function. If we took these three statements and just replaced all of the u's with x's, we would have those original three rules. And so those still apply. U could be our variable. Everything still works just like it was before, but U can also be its own little function. So the chain rule comes from composite functions where we have a function inside of another function. So that's what we're seeing here again. We have u to the n, e to the u, 1 over u. Those are all sort of exterior functions, and the u could be another interior function. But those three rules are still going to apply. We're just going to have to do a little bit of work in order to use these rules when u is a function itself. So there is a procedure in the book, also on page 355, with 4 steps to the substitution method, which we are going to go through with a couple of examples. So here is our first example. And I have the 4 steps written or typed on the screen, but these 4 steps are on page 335. As well. So these steps might not make sense at first when we're just reading them, which is why we're doing an example. So the first step, as it's written in the book, is to select a substitution that appears to simplify the integrand. So remember, the integrand is everything in that sandwich between the integral sign and the dx. And we want to select u so that du is a factor in the integrand. So that sounds a little confusing at first. What we are looking for is that sort of undoing of the chain rule that we saw at the very beginning. So looking at this, I'm just going to rewrite it so I can make some notes on it. We have this sort of complex stuff to start out with. There's these parentheses with a bunch of stuff in them and the 5th power on the outside. And then we also have a little bit more multiplied, that 12x cubed. So the thing that we're always looking for when we do substitution is to notice that this 12x cubed is the derivative of this inside part. So our goal is to get this integral that is complicated looking right now to look like one of the rules. I'm going backwards for a second. One of the rules here. So we're going to try to simplify that integral a lot so that it fits one of these three situations. So the substitution part means that we're going to find a u, which is going to be its own little function, so that du is a factor in the integrand. So du is just the derivative of u with a little dx at the end.
So do you just replace x's with u's?
Not quite.
Okay.
So u is pretty much always our interior function. So if we're looking at just the first part of this integrand, the part that's a little more complicated because it has the parentheses and that fifth power, our interior function is that whole 3x to the fourth minus 3.
And is that all? That's always
Yes.
okay?
Sometimes
Okay.
it might take a little bit of working to figure out what that interior function really is. But yes, the u is going to
Okay.
be the interior function. And the way we check to make sure we have a good u is to find that differential. So ignoring the integral for a second, we just want to find du based on the u that we just found. So if u is 3x to the fourth minus 3, du is 12x cubed dx. So we need to choose u, which is generally the interior function. But we have to make sure that u works, and we do that by finding the differential, the du. And this part, so that du is a factor in the integrand. Du in this case is 12x cubed dx, and that is all in this integral. So that's good.
And so you're saying that the second factor is always going to be a derivative of the interior?
It won't always be the second factor. It could be out of order. But yes, some factor in here should always be a derivative of the interior. So that 12x cubed could be out front, and we will see that in some later examples. But as long as that du is there as a factor in our integral, then we have a substitution.
Real quick, Madeline, that's why you underline that du is a factor in the integrand, because it's literally a factor in the integrand.
Yes. Yes.
That makes that, I don't know how it makes sense, but it does. It's kind of crazy.
Good. Glad. So the whole point to this, so this starts off looking and feeling messy, but good things are about to happen. And let me see what step 2 is yeah, okay, so I don't want to get ahead of myself. So the whole point to finding that u and the du is this step 2. not right. So our second step, and you don't have to write all of this out again, I'm just writing it out so it's in the second step area. Our second step is to express the integrand entirely in terms of u and du, completely eliminating the original variable and its differential. So when we are done substituting stuff, we should have no more x's left in this integral. So we said that u is that 3x to the fourth minus 3. So this integral, instead of having that 3x to the fourth minus 3, is going to have a u to the fifth power. So that whole interior part is being replaced with a u. And then we also found that du is equal to 12x cubed dx. So that whole 12x cubed dx gets to be replaced with du. And now we have such a simpler integral to work with. So the whole point of step one of choosing that u so that du is also in our integrand is the setup for being able to replace everything in our original integral with stuff in terms of just u. So now instead of having this big mess of an integral, we have just u to the fifth, which is something that we have been doing in our previous problems. Those two steps are it's usually more like step one is kind of the tricky part, just figuring out what u needs to be. Once we have everything in terms of u, our integral is pretty nice. So I'm going to bring up step 3, which is to evaluate the new integral. So if we're evaluating u to the fifth du, what is our result?
U to the sixth divided by 6
Exactly.
plus c.
Let's see.
Right. So that was so nice. Our integration was just like that little step. And we have just one more step. So the original problem was in terms of x. So we can't have our answer just with these u's. So we need to go back. There it is. Oops. Having scroll problems. Okay. So we need to, step 4, express the antiderivative found in step 3 in terms of the original variable. All that means is take this and put it back in terms of x. So if our answer was u to the 6 over 6 plus c, and we know that u was 3x to the fourth minus 3, we just have to put 3x to the fourth minus 3 where u was. So this answer we got in step 4, that's similar to that very first example from 5.2 where we did do the chain rule first and then went back to the integral. So we have this thing in the inside with an exponent. And so if we were to take the derivative, we would do the exterior by multiplying that 6 down and lowering the power by 1. And then we would multiply by the interior and we would get what we started with inside this integral. So U substitution is tricky, but it's really nice when we get the hang of it because we're starting with this messy thing and then we have just this cute little integral to apply one of our rules to, and we can go back to x in the end.
Hey, Madeline, do you mind scrolling down a little bit?
Yes. Oh, there's nothing there.
Okay. I couldn't see the u equals 3x4 minus 3.
I just wrote that there, so it's handy. That's the same u we used before. Let's do one more example. So I don't have the rule or the steps written down here, but we can just verbally talk through them. So our first step is to choose u.
T
Is
to
it
the
T to
third
the third
plus 4.
plus 4.
Yes, good, t to the third plus 4. And so anytime we choose a u, even if we are pretty confident that that is going to be the u, we always need to make sure. So when you are looking for, when you're finding du, don't look at the original integral, just find du based on the u you chose, and then check to see if it matches the integral. Because I sometimes see people choose a u that's not quite right, but then their du is correct, and then things get mismatched. So we're choosing u and then finding du based on that u we chose. So our u is t to the third plus 4. Derivative of t to the third is 3t squared. The 4 goes away. dt in this case. So we chose what looked like a good u. We found du. And then we should go back and just see if everything matches up. So u is this t cubed plus 4, and that is in that interior part of our integrand. And our du is the 3t squared dt. And this is an example of where that 3t squared and dt are separate in the integral, but that's okay. Each of these still together make up that whole du.
What happens to that -2?
That is staying there.
Okay.
So that's part of the like exterior function, if we're thinking in terms of exterior and interior. So when we put this together, the u is that whole t cubed plus 4, and that will still have that -2 exponent on it. So that's sort of like our exterior function that's being left, and that's what we will end up actually integrating with the u. But then that whole 3t squared dt is being replaced by u. So we have our u, or excuse me, du. So we have our u that came in and now has the -2 as an exponent, and du is that whole 3t squared dt part. So that was steps 1 and 2. So step 1 is choosing that u and making sure the du is going to work. Step 2 is replacing everything from the integral with u stuff. Step 3 is doing the integral. So what will be
T3 plus 4 to the -2.
let's no, not yet. I'm sorry, I had to process what you were saying first. We need to first, before going back to t's, we need to find the integral of the u to the -2.
A u -3 over -3.
Almost.
U to the -1 over -1.
Right, exactly. So we have to be careful with that adding 1. So -2 plus 1 gives us a -1, which dividing by -1 just means we have a negative u. So now, after integrating the thing with the u, we can now go back to our original variable. So we have that negative on the outside. Oh,
Madeline, real quick, would you want to put that -1 into a fraction to make it a positive one for the exponent?
It doesn't really matter if you want to, it is totally fine. The reason that I wasn't going to on this one is just because our original integral had, had it with a negative exponent.
Okay, understandable.
But there's no like exact answer. Either way is fine. So we can leave it as negative t cubed plus 4 all to the -1 plus c, or we could put it like this. That's just one of those things, like when we're doing derivatives, like in the context of graphing, we want to have positive exponents so that we can evaluate and solve and things like that. In this context, either of these is totally fine. They both work. So you do not have homework due next week because you have the test due on Tuesday, but I am planning on posting the first part of the next homework today, just in case anyone is feeling ambitious and wants to get started on it, but it will not be due until April 6th, which is a week from next Tuesday. So it'll be there, but the test is the important thing at the moment. So we will do a little more practice with substitution on Tuesday and then continue with integration. And we'll have our 20 minutes of Q&A also. So have
Thank you.
And yeah, thank you. See you all next week.
See you next. Bye.
Thanks.
You're welcome.
You can't see, but it's starting to blizzard again outside.
Oh, good.
Right? Never
We'll
can
probably
tell.
go home and put on sweatpants after this then.
Oh, yeah, I got blankets and a cat here, so I'm pretty good.
Madeline, I just had another quick question.
Yeah.
This was regarding the graphing thing with the test. I just wanted to know if you said there's other options besides the quadratic formula and completing the square. What else was there?
So quadratic formula and completing the square are the only ones for that problem.
Okay, I thought so. I was like, there's another one I would like to know.
Yeah, factoring, but this one isn't factorable, and then the square root property, which doesn't work here either because there's that 3x.
That was
So
a good question, though.
Thanks. And factoring. All right. All right, Madeline. I'm actually switching places with you. I got to get dressed and go there.
oh,
All right. You have a good day.
you too.